everybody, and welcome back to Digital Integrated Circuits. I'm Professor Adam Teman of the EnICS labs at Bar-Ilan University, and today we're going to be going over the Kahoot for Lecture 3, MOSFET Modeling. So let's get started. In today's lecture we have 10 questions. The first is, which phenomenon is not taken into account by the square law model as it's presented in the lecture? Is it linear operation, pinch-off saturation, velocity saturation, or channel length modulation? And in the picture we have Shockley, Brattain, and Bardeen, who invented the transistor and got the Nobel Prize for it. And since I called this the Shockley model, this is William Shockley. So the answer is velocity saturation. And let's go back and see how that came in our here. So we see the square law, or what I call the Shockley model. Actually, it takes replacing VDS with a VDS effective, which would be the minimum of VGS minus VT and VDS. If VDS is minimum, that means we're in this area of the graph of VDS versus IDS, and that's called the linear area. And if we're in where the minimum is VGS minus VT, that means we're beyond this VGS minus VT or VGT point. That means the channel is at pinch off, okay? And we are actually over here in the saturation area. And in that case, we just take the VDS effective and put it inside this one equation that rules them all kind of thing. And if we're actually in saturation, we put VGS minus VT over here, and this becomes VGS minus VT squared. So we get this square relationship of the output current IDS as a function of VGS, because VT is a constant in this case. So we get this quadratic relationship. Okay, so that is why it's called the square law model. And actually, in the original Shockley model, we just had this type of a constant saturated current, an ID sat over here, which was later fixed by the Shichman-Hodges model to have a linear kind of increase in the IDS according to VDS. So in the Shichman-Hodges model, we also take into account the pinch-off, the channel length modulation. I just want to mention the Shichman-Hodges model from 1968 is actually SPICE level 1. So if you go into the SPICE parameters and put level 1, you will get this simple model. Okay, it does not take into account, however, velocity saturation, and that's why our answer over here was velocity saturation. It has linear operation, as we saw. It has the pinch-off saturation over here, and it has channel length modulation, at least in the Shichman-Hodges model, but it does not take into account the velocity saturation. Our second question is, mark the incorrect relation. Is it that the current in saturation is affected by VDS, the saturation voltage, VD-sat, is affected by channel length, the on current of the VT star model is affected by VDS, or the current in the alpha power model is relative to VGS to the power of alpha? And the answer over here is going to be this yellow one. And let's go back again to our slides and just kind of see an overview of some of the models that we saw. So we saw that the Shichman-Hodges or Shockley model, it has this square law that gets a pinch off at VGS minus VT, and then we have the channel length modulation effect that is taken into account by it. Velocity saturation comes because of we have our velocity of our electrons or our holes is relative to the field that is applied to them, and it has to do with the length of the transistor, and at some point it saturates and stops getting longer. So we have velocity saturation has the L over here in the relation, and so that is actually the saturation voltage has to do with the length of the transistor. So VD-sat is a parameter of the length. The VT star model is a simple model that is used for kind of digital type of things, where we usually have VGS is either at VDD or it's at 0. And when it's at VDD, we are in velocity saturation for sure in modern kind of short channel transistors. So as long as we have a cutoff area when VGS is really low and a velocity saturated when VGS is really high, close to VDD, we can simplify our whole model by making it piecewise linear, and then we say that This point here is VT is called VT star. It's at VT plus VT sat over 2, and then we get just this really piecewise linear type of curve, which is really easy to use for hand calculations. So that's our VT star model. It is not dependent on VDS because it assumes that VDS equals VD sat, or at least VDS effective equals VD sat. Finally, the alpha power law model is kind of a nice model that comes and looks at the square law model and says, listen, when we use the square law model, it's not that accurate, but if we change the power, instead of being 2 to something else, for example 1.3 in this kind of old technology, we see that there's a much better curve fitting that we get over here from measurements. So that's the alpha power law model, and keeping it at something that's similar to the square law model also helps us do some hand calculations. So going back to our Kahoot, we see that the current in saturation is affected by VDS, and that is taken into account by the channel length modulation. The saturation voltage, VD-sat, is affected by channel length. And yes, saturation voltage we saw is a parameter of the channel length. The current in the alpha power law model is relative to VGS to the power of alpha. That's exactly what the alpha power law model is saying, but the on current of the VT star model is not affected by VDS because VDS is assumed to be a constant VD-sat. So that is our answer of the incorrect relation. Okay, question number 3. Which is the most accurate of the various MOS models? The piecewise linear model, the square law, Shockley or Shichman-Hodges model, BSIM 3.3, or the alpha power law model? And the answer, which we can kind of have a hint here because this is one of the gates at the entrance to Berkeley, is the BSIM 3.3. Let's go over to some of our newer models, and BSIM really has been the workhorse of models for the last several decades. It's the Berkeley short channel IGFET model, and it's really the primary compact model that's used for SPICE simulation in the last 3 decades. So at Berkeley first they invented SPICE, and then they decided to go and develop some compact models that would really be really good at taking into account transistors that were getting with more and more phenomena as the channels got shorter. And that's where the BSIM models were started, and the BSIM group that develops it was started. Okay, these models, they use hundreds of parameters to achieve a good fit. In BSIM-4, you would have something like 400, 500 parameters, I believe. There's a nice user manual that has all the equations and explains how it works. And really, it was the main model for bulk CMOS until like 28 nanometers or so. And then they started going into things like BSIM-5 and so forth, but actually that's when the world moved over to FinFETs, and really BSIM-CMG took over, and that's kind of the workhorse now for FinFETs. For FDSOI type structures we use BSIM-SOI, and there are other models that are popular like PSP or EKV, which is a popular subthreshold model, and there's a coalition called the Compact Model Coalition that really chooses and maintains and promotes new models, and there's kind of a competition between the different groups, but Berkeley does seem to be really leading this with their BSIM, even now in the multi-gate type of era, which we'll be discussing in the further lectures. So of course, going back to here, piecewise linear model is a real simple model. It's just taking, you know, straight lines and fitting them to our curves. The square law Shockley model, we said, is a pretty simple model that, or the Shichman-Hodges model is level 1 of SPICE, whereas BSIM is higher levels of SPICE. And the alpha power law model is a kind of a try to make a curve fitting that would provide something better than the square law model. But BSIM and 3.3 is already an old BSIM, but it really does a lot of, it has many parameters to help us base both physics and curve fitting to meet the measurements. So, which of the following is used to fine-tune the threshold voltage during fabrication? The work function between the gate and the substrate, the Fermi level of the substrate, the amount of charge trapped in the oxide, or the depletion charge implanted in the channel. And the answer here is going to be the green one. Again, let's go back into our slides. And we have to remember about threshold voltage, and there are several things that we had here. So the basic threshold voltage, VT0, was set first of all by the work function between the metal and the semiconductor. So a work function of a material is the distance between the absolute vacuum and the Fermi level. Okay, so that's going to be the work function of, sorry, I drew that wrong. It's going to be the work function of the gate material, which is actually not a metal, it's polysilicon. Nowadays we've gone back to metal gates. Okay, and the work function of the semiconductor is going to be something different. So the difference between them, which is going to be this size here, that is going to be our phi-ms. That's the metal to substrate or metal to silicon work function difference. So that's going to be the basic thing. It's decided by whatever materials we use on the two sides of the gate oxide. Then we have two phi Fermi. So the Fermi level, again, that's the energy actually that when we start out, our p-type semiconductor is going to have its Fermi level rather close to our valence band. And it's going to be the distance of E Fermi away from it to go and change this into an n-type semiconductor, which is what we want to do with inversion over here around the gate. What we want to do is actually bring our semiconductor, change it from being here to having the Fermi level over here. So if we look at this side, we have the Fermi level is going to be closer to the n-type, the conduction band, and then it becomes n-type. Okay, so what we want to do is we want to move it first one E Fermi to be flat band, and then another E Fermi we want to bend it some more to become an n-type semiconductor for inversion. So that's our 2 phi Fermi, and that's again a question of our doping levels of the two sides or the differences between the two sides, and how much actually voltage we want to put onto the channel in order to bend the bands. Then we have things like Qox over Cox, which is actually the amount of charge that we have accidentally stuck inside the oxide and it bothers us, and the depletion charge that we have under here that we have to get out of there to reach depletion. But the other one is the important one that I wanted to talk about, which is our implant charge. And this is actually a free parameter that we use to change the threshold voltage. So we can put more or less charge and charge of different polarity to actually adjust our threshold voltage for high VT transistors, low VT transistors, and just small adjustments. And actually that's the biggest problem of variation in deep planar transistors because of the random dopant fluctuations. So let's go back over here, and we had the work function between the gate and the substrate. So that for sure is one of the parameters of VT, but it's not something we use to fine tune. That's basically the characteristics of the metals. I just want to tell you that actually in FinFETs we use this work function to do this setting of to fine tune the threshold voltage by using different metals there. But that's not what is done in traditional planar transistors as we discussed here in the course. The Fermi level of the substrate, again, we have to change it to 2 phi Fermi, but it's not something that we are able to play around with in a fine-tuned type of way. And the amount of charge trapped in the oxide, that's actually a parasitic effect, and we want it to be as low as possible. But the depletion charge implanted in the channel is the parameter that we use to fine-tune the threshold voltage. So that was the right answer. Question number 5. Which of the following sentences is true about the body effect? First, negative voltage on the body of an NMOS lowers VT. Second, the larger the depletion cap, C dep, the smaller the body effect. A positive voltage on the body of an NMOS lowers VT. And the body effect is quadratically dependent on VDS. Well, I see that these two are exactly opposite of each other. So is it that negative voltage on the body of an NMOS lowers VT, or does positive voltage on the body of an NMOS lowers VT? And I'm going to tell you that this is the answer, and that means the other ones aren't. So let's just go over to the slide a minute, and I'll show you how I kind of remember these things. So there are several ways that you can kind of play with to remember it, but if I take my NMOS transistor, let's say, so I have N plus and N plus diodes over here, and the gate oxide and gate voltage over here, and the gate electrode over here. So I have a diode over here, and what I know is that I need this diode to be reverse biased. And how do I get that? Usually I have ground over here, and I have something that is larger than than 0 over here. It can be ground or it can be larger, and that keeps me with this reverse reverse bias on this diode, and there's no problem. Well, I always remember that I can reverse bias a diode quite a bit. Okay, and reverse biasing the diode, it's not going to make the transistor faster, it's going to make it have a higher VT. Okay, so what does that mean? It means I can actually lower this down to something negative VB, okay, and that's going to increase this without somehow turning on the transistor, and that's going to cause VT to go up. On the other hand, if I want to go and put some sort of a plus VB over here, right, I'm going to make this a much smaller. In the end, if I go, if this is going to be 0 and I'm going to have a plus VB, we're going to have this positive voltage, which is going to turn on the diode, and our transistor is going to, get into a latch-up type of thing. We're going to have a current going through the transistor the wrong way, through the diffusion. So I'm not allowed to do that much. And I know that I'm really not allowed to do this much. What it does, though, is it causes VT to go down. So I always remember that a positive voltage, which I can't do a lot because it turns on the diode, is what helps me get a faster transistor by making this go down. So that's one way to remember it. Another way is just if I look at my NMOS, and again I take my NMOS because it's kind of the basic thing, we do everything opposite. For a PMOS, I can put as much, or not as much as I want, but a lot of reverse bias, and that's going to make my VT go higher. In general, I have kind of an EnICS rule that says that anything that we can do is going to make things slower. So we have hot electrons that are going to make things slower. Reverse body biasing, which we're allowed to do, is going to make things slower. If we could do things that are going to make things faster, like forward body biasing, then we're going to be limited in how much we can do it. So that's kind of something that I use to remember how reverse versus forward body biasing affects the VT. That being said, first of all, in more modern technologies, the VT has become quite a linear type of dependence on the voltage output on the body, number one. And number two, it's actually the factor has become very small. So we can hardly change VT. And with FinFETs, it's almost non-existent. Another thing that I want to tell you is that we actually want to get rid of this body bias, because the body bias is part of how we kind of ruin the control over our channel. So in general, what we want from a transistor, so traditionally we have our transistor, we have our gate oxide over here, and there's the gate. This we can call it C for channel, that's the voltage we have over here, right? And this we'll call B, for body. And what we want to do actually is we want to change the channel voltage by 2 Fermi energies in order to cause inversion over here on the channel. And how we do that is by applying voltage over here to the gate, right? So what we want to do is we want to have some transfer function of voltage from the gate to the channel. And there is a capacitor here. This is, an electrode and a dielectric and another type of electrode. And so what we're doing basically is we have this capacitor, which is this CG2 channel, right? And this is G, this is the channel, which we can't actually touch, but we can kind of like look at it. Okay, and we want to have anything that we put on here, any voltage that we put on here, plus VG, apply to our channel. The problem is that there are other capacitors over here. One of them is CGB. Okay, another one would be our capacitance to the drain and our capacitance to the source. So we have all these other capacitors here, CGS and CGD. Which are bothering us, because when we try to pull our transistor to VT over here, these guys are holding it to a different voltage, and that's something we don't want. We want to have total control with our gate terminal, okay? And these guys are really fighting us. So what we wanted, and that is actually our subthreshold slope, which we're going to talk about, discuss leakages. We want to fight that. We want to combat it. We want to take it down, okay? So really, actually in FinFETs, that's kind of what we do. With FinFET transistors, we have our gate, right? This is the going over our fin, which is this. So here we have the current running over here. And now we have capacitances from all three sides, which is a lot more capacitance, and the capacitance of the body is only at the bottom. So we get a much better control. We get the CGC getting much larger than the other parasitic capacitances, and that's what we want to do. We want to have this as big as possible and all these guys as small as possible, and that reduces our body effect and gives us more control over the gate. That's what actually happened in recent technologies. So let's go back to our Kahoot and try to understand why we said, so I explained why a positive voltage on the body lowers NMOS VT. I didn't actually explain it, that you can kind of see in old semiconductor courses that I've done, but that's just how to remember it, that a negative voltage on the body actually increases VT. So out of these two, only one of them was correct, so it was easy to choose one. But what about the other two answers? Why are they not correct? So the larger the depletion cap, C dep, the smaller the body effect. And exactly what we said over here is we want this to be smaller, okay, to use the body effect, or the larger it becomes, the more control these guys, which could all be called C depletion or something like that, have over the channel. So so again, the larger the depletion cap, the smaller the body effect. And the final answer over here was that the body effect is quadratically dependent on VBS, but as we saw before, it's actually more linear dependent on VBS in deeply scaled technologies. So it's not quadratically in any case. So that was this question number 5. Question number 6. Mark the incorrect sentence about hot electrons. Hot electrons occur close to the drain depletion region. Hot electrons cause fluctuations to VT during fabrication. Hot electrons cause the threshold voltage to rise over time, or hot electrons are considered a reliability issue. So which one is incorrect? Well, let's see. It's this one. And how do we know that? Well, let's go back to our and what are hot carrier effects? The hot carrier effects are that electrons get so fast that they can tunnel into the gate oxide and increase the threshold voltage. So what happens is that we first put a gate voltage over here, and we cause these field arrows to appear over here, and they create the inversion inside the channel, right? They pull the electrons over here and cause inversion. And then we put a voltage over here, which actually causes the voltage drop between the drain and the source and causes the electrons to fly across. And they get energy, and they're being pulled, and they also, sometimes jump against the interface over here. But when they actually get to the drain, they reach the depletion region of the drain, and they get pulled really strongly inside the field of the depletion layer. And that gives them a ton of energy. And at the same time that they have a ton of energy over there, they're being pulled up by these, these field arrows over here. So what can happen is there's a non-zero probability that they will get enough energy to jump over the energy barrier that we have on the gate oxide, and some of them will go over into the gate and then just keep on going, but the other ones will get stuck trapped inside the gate oxide and increase the charge, and then we have this QOX, COX. It grows over time, and what that does is, again, according to Adi's rule that I mentioned before, it causes VT to go up in both an NMOS and a PMOS, or VT in a absolute value to go up. So it causes eventually the transistor to go slower. Now this is a reliability issue. It happens when we use the transistor where you have a lot of current going over time through here with a high drain voltage, and there's a higher probability, since we have current going for a lot of time, that every once in a while one of these charges will get stuck. So it's a reliability problem. And that is exactly the answer to the Kahoot. Hot electrons cause fluctuations to VT during fabrication. No, it doesn't happen during fabrication. It's not a fabrication issue. It is a reliability issue that happens over time. It's an aging type of an issue. Okay. Other answers: hot electrons occur close to the drain depletion region. Yes, they actually occur usually inside the field of the depletion region of the drain, where we have a big, strong field over there. Hot electrons cause the threshold voltage to rise over time. Yes, this is what they do. They get stuck inside the oxide and cause the threshold voltage to rise. And hot electrons are considered a reliability issue. Yes, they are a reliability issue. They're not a manufacturing issue. Okay, question number 7. Mark the correct sentence about the short channel effect, SCE. Short channel effect is a rise in drain current due to VDS. Short channel effect is a drop in VT due to channel length. Short channel effect is a drop in drain current due to VDS, or short channel effect is an increase in VT due to channel length. Well, again, we have these two which are exactly opposite to each other, and these two are also opposite to each other, but the only one that is the short channel effect is the channel length effect on VT. So let's Go back to the slide about short channel effect. It's also called VT roll-off, and that kind of tells us that really as we have this type of graph which has this kind of drop at some point, that's a roll-off. So really, as we can see in this graph over here, we have the channel length, and as the channel length goes down, we should have no dependency of VT on channel length, but when we get to short channel lengths, it drops off. Now, why does that happen? And we can look at it in a few ways. Well, one way to look at it is this type of graph over here, where we saw that we have the source and the drain and the gate, and we have this potential barrier which causes the electrons that are over here in the source not to be able to run across the channel, even though we have a voltage drop between the drain, which you see has a lower energy than the source over here, and wants to pull these electrons, but they're blocked by the gate potential barrier over here. And what happens is when we put some voltage on the gate, the energy level over here of the gate goes down, and when it gets down low enough, then these electrons can fly over here. So that what we want to do is we want to have this high, and then be able to put some charge or some voltage over on the gate to move it down until it's low. What happens is when we make the channel shorter, the drain is pulling the energy down below. The source is pulling it to this area, right? And the gate is trying to pull it up. But when we get real close, like over here in the blue one, you see that the energy is still affected by both the source and the drain, and isn't able to get to the full level that we had before that was supposed to cause our VT level. And so VT goes lower, and as we go lower, we lose control of the gate over the actual channel area because the channel is so short. So that's one way to look at it. Another way is looking at the parasitic, I would call it, control of the channel by the source and drain. Is similar to what we saw over before with CGD and CGS, but we have the depletion regions of the source and the drain, which are actually, they're not, independent of the channel. They're eating away from the channel area, and therefore the amount of charge that we have over here that we have to move over and bring in minority carriers instead, it's less because we have this trapezoid type of a thing over here, and it's less than what we would have had if we had the perfect kind of a rectangle. And as we get shorter, the sides of the trapezoid become a larger amount, and the actual amount of charge here is much lower than our rectangle, which could be the amount of charge we have to move out of there for VT. So that's another way of looking at it. In any case, what happens is that we reduce the length, and VT is reduced. That's the short channel effect. So the answer over here was short channel effect is a rise in drain current due to VDS, or a drop in drain current due to VDS. And no, that's actually a different phenomena, and that's the phenomena we call Dibble, which we see here with two different VDSs, we have different VTs. But so that's Dibble, that the effect of rise or drop in drain current, or VT, depending how you want to look at it, due to VDS. The actual short channel effect, or VT roll-off, is a rise or drop in VT due to channel length, and the correct relation is that it's a drop in VT when the channel length goes down. Okay, so that was our answer over there. Question number 8. 3 sigma means that what percentage of the samples fall inside the range? This was just a quick reminder about probabilities. Is it 97.7%, 99.86%, 99.996%, or all of these 9s over here? How many of that? A lot of them. Well, no, it's going to be 99.86%. And let's go back to our slides and just remember. So remember that we're going to be using a lot of normal or Gaussian distributions, and a normal Gaussian random variable that's shifted to have a zero mean, and a normalized standard variation of 1 is going to have this type of a probability function, right? And this type of a CDF with this error function, and it gets these the CDF over here and the 1 minus f of x over here. And usually what we try to do is give a few certain numbers that we can remember and think about. And the two that are very important to us are the 3 sigma point and the 6 sigma point. And the 3 sigma point means that 0.998650 of the samples, they fall inside the 3 sigma. So when we get to 3 sigma, we get really a very high number of the samples over here. Okay, and that means that basically 99.8% of our samples will fall inside that area at 3 sigma. Why is 3 sigma very significant? Because we usually set our process corners to be where the transistor, where 99.8% of the transistors are fabricated, and we go and we take the most, the worst case, if it's slower or faster of these, and that's where we set the parameters to figure out where most of our fabricated devices will fall, and that's to get as high a yield as possible, to have as many of the things that we fabricate will actually work. So that's why we take 3 sigma as kind of the place where we put our global corners. On the other hand, when we have structures that appear a lot like memory cells, 99.8% is not enough. If we have 1,000,000 cells, 99.8% is not enough, because a lot of them will still fail. So we take something much higher, and there we take usually a 6 and even an 8 sigma type of point. And in 6 sigma, only 1 in 1,000,000,000 will actually fail. So if we have 1,000,000 of them on a chip, that's okay, maybe, because only 1 in 1,000 will fail. But we can even take a higher number like 8 sigma to have even a better, yield. So that was our answer. 99.86 is the 3 sigma point. Question number 9. What is typically defined as a fast corner without temperature inversion? Is it process fast, temperature 0 degrees Celsius and voltage VDD minus 10%? Well, process, I gave you FF on all of them, because probably in a fast corner we're going to have the fast process. Temperature 125 degrees in VDD minus 10, temperature 125 degrees in VDD plus 10%, or temperature 0 degrees and voltage VDD plus 10%. And this is without temperature inversion, so the process is going to be really over here. Okay, so in other words, it's going to be fast with a low temperature and a high voltage. So let me go back into the slides about that. So we had this table which kind of shows us what our process corners are made up of. So what we have is we have PVT, process voltage and temperature. These 3 plus other parameters are going to be the process. Okay, these guys are going to be the process. This is the voltage. And this is when we take into account, well, let's start with the voltage because it's kind of easy. When we want things faster, we want higher voltage. So for a fast corner, we're going to take plus 10%. And for a slow corner, we're going to take minus 10% on the voltage. And that will ensure that when our battery gets tired, or we actually overcharge the battery, or we had an irregulated type of a voltage source, we're still going to meet our setup and hold timing constraints that we're going to be discussing in a future lecture, or whatever the characteristics of our custom block, our analog block is going to be. For temperature, what happens is when we raise the temperature, we heat up the atoms in the channel. So the atoms, they actually have this type of motion, Brownian motion and stuff. They're going to be moving around all the time. So they have some sort of probability of moving around, and the more energy we give them by more temperature, the bigger this gets. Okay, and they're moving around, and then we have a nice little electron over here that wants to run from one side of the channel to the other. Since these atoms are moving around faster and all over the place, there's a higher probability that it's going to run into them and it's going to slow down its overall speed. So basically, when we raise the temperature, so T rising causes the mobility to go down, and therefore when we go to a fast corner, we want to take a low T that's going to cause the mobility to go up, because then we're going to have our atoms are going to be place, and then our electron's going to be able to really fly across there. So for a fast corner, we're going to have a low temperature. Okay, and for a slow corner, we're going to have high temperature. And really, we usually take for our temperature ranges, we'll either do from 0 degrees Celsius to 85 degrees Celsius, or a more harsh one, which takes minus 40 degrees Celsius to 125 degrees Celsius. Okay, so those are our kind of temperature ranges that we use. So for a fast corner, it'll be 0 degrees Celsius or minus 40 degrees Celsius. For a slow corner, it'll be 85 or 125. Okay, these three over here are kind of three of the most important ones that cause our process, RP, which is how the transistor is actually manufactured, and not the operating conditions, which are VDD, the voltage and the temperature. So VT, so obviously VT, the lower it goes, the faster our transistor is going to be. So in a fast corner, we're going to have VT go down, and so we're going to take, this is going to be VT, and this is going to be the probability, the percentage of samples that came out with a certain VT. And if this is the nominal VT, this is the kind of VT nominal, we're going to have some sort of Gaussian that's going to describe how VT is distributed. And we take a 3 sigma point over here, and that's going to be, that's going to be the fast corner. And we take a 3 sigma point over here, and that's going to be the slow corner on VT. So the fast corner is with a low VT, and the slow corner is with a high VT. With L, again, we have our, our transistor is going to have the L over here, and if this is closer to here, we're going to have less of a distance, and so the transistor is going to be faster. So L going down is the fast corner, L going up is the slow corner. And for the oxide, the oxide, C-ox is E-ox over T-ox. Okay, so we want C-ox really gives us our transconductance. For a higher C-ox, what we want is a lower T-ox. It basically improves or makes the capacitance, or improves the control over the channel, improves the transconductance. So for a fast corner, we're going to have a smaller T-ox, and for a slow corner, we're going to have a higher, a larger T-ox. When we get to temperature inversion, what we're going to do is we're going to flip around these guys, because VT, which goes down with temperature, is going to overtake mobility. But I'll be discussing that later. And last question, what is Pelgram's law? Is it that VT is linearly proportional to transistor length? It's that it's inversely proportional to transistor area, that it's inversely proportional to transistor length, or linearly proportional to transistor area? So the answer is going to be that VT, or at least the distribution of VT, is going to be inversely proportional to the transistor area. So let's go back over here and just remember about Pelgram's law. So Pelgram's law discusses about how local variation kind of is affected by transistor size, and why variation gets a lot worse as we lower our as we scale our transistors and get smaller and smaller transistors. So basically the problem is that we need to stick dopants into the channel over here in order to set our VT. And if we have to only put 170 dopants in over here, and we have a few more, we have 200, and here we only got 150, we're going to have different VTs, and that's going to cause a large variation. If we had a huge transistor like in the past, we may have millions or something of dopants in here, and then if we have a small difference, plus 100 or plus 1,000 dopants, it's not going to make any difference in our VT. So really the sigma, the distribution of VT, is going to be proportional to the width and length. It's also true about our line edge roughness and our line width roughness and so forth. They're also going to be proportional to the area. So Pelgram's law really shows that the variance of our VT, and altogether how our transistors are affected by variation, is going to be a inverse factor of the area of the transistor. Again, VT is inversely, or at least sigma VT is inversely proportional to the transistor area, and not only to transistor length, and it for sure isn't linear. So basically that was the end of our Kahoot for today, and if you have any questions, as always, please ask me on my YouTube channel.